Okay, good morning everyone. Good morning. So you'll have your first midterm exam this week. A couple of words about the exam. I think there's some confusion on what the times are. So here are the actual times. Opens on Thursday, let's say morning 9 o'clock. And because some of you want me to keep the exam available for a longer period of time, I'm going to have the exam open until Friday. (11:59 p.m.) Okay. So what this means is, of course, you're not going to have 2 days for the exam. In between Thursday 9 a.m. and before Friday 11:59 p.m., you select a 4-hour window. Okay. And you write the exam during this time. Does this make sense to everybody? Any questions, doubts, or clarifications on what this entails? So between these 2 days, you can select a 4-hour slot. On Friday, we will have lecture as usual. You're welcome to come. You're also welcome to watch it on YouTube or whatever, the video that I'll post. Friday, business as usual. And for the exam itself, we have a practice exam that has been set up. A couple of words of caution. A practice exam means it is for practice. Does not necessarily mean that the actual exam is going to be the same thing. Okay, the actual exam may be harder or may be easier. That is completely subjective. Depends on your preparation, depends on a lot of circumstances that fall beyond my control. But what I can guarantee, some of you have taken my classes in the past, what I can guarantee is that the exam will be fair, the grading will also be fair. Okay, if the exam is tough, my grading will be taking that into accordance. Right? So probably 3 questions. One of them very short, and the other 2 medium, not long. Okay. Now the practice exam is a very good indicator of the length of the actual exam. And then on Tuesday, tomorrow, at 6:30 p.m., 5:30 p.m. to probably 7, but I'm hoping it won't go until 7. Because I'll be answering questions and so on. I will have a midterm review. On Zoom. I will send the link tonight. All your exam solutions, practice exam solution and homework 5 solutions will be uploaded by Wednesday. Okay, once you submitted homework 5. Alright, any clarifications? Yes?
Should we need the entire 4-hour window?
Oh, definitely not.
Okay.
So here is the thing, okay? If I am given 4 hours to write an exam, and if I have those 4 hours, I will use all those 4 hours. That's the human mentality. right? So tomorrow you come and tell me that, hey, I used all the 4 hours because your exam was long. My answer is that is not necessarily the case. It is because the 4 hours gives you some time to think, to answer the questions in a deliberate manner so that you're not rushed, you're not stressed, and so on. And I've seen in the past, I mean, I've had 6-hour exams, 5-hour exams, I've had 3-hour exams. 4 seems to be like this nice baseline number. It's not too long, it's not too short either. And in my opinion, an exam of this sort should be completed within an hour, hour and a half max. Okay? Yes, sir.
The Carmen quiz setup, is it gonna be like upload work for each question?
No, just okay, upload only once. Upload your answers only once. You have only one attempt for the exam. That's very important to understand. There's only one attempt for the exam. I'll be sending you a whole list of all these exam details and so on later tonight. You upload your answers as one single PDF. Okay? And the Carmen quiz is the only format that lets me have a timed window for the exam. Otherwise, I would have given you a Carmen assignment where you just drop your stuff in there. And we'll see how things go. If after the first midterm exam, some people believe maybe this 4 hours is an artificial time constraint, why not give me the whole day? Maybe I'll think and say, okay, take the whole damn day. We don't know, right? So we'll see. Okay? We'll play it by the ear. I'm getting to know you as you're getting to know me. The first exam is an opportunity for me to see how much we have synced together. Alright? Yes, question.
Will that Zoom review be recorded?
Oh, absolutely. Everything I do will be recorded. It also holds me accountable. Alright, any last questions before I proceed with the lecture for the day? Alright, so we'll move on. I think I started looking at the critical radius of insulation last class. I'll complete that. And then we will move on to the idea of heat transfer from extended surfaces or fins. Okay, well, an important application of conduction heat transfer. Okay, from last time, we had the following problem. I'm not going to look at the numbers again. We're not going to solve anything again. I'm just going to set up the drawing for it. So hollow. This was a steel pipe of thermal conductivity K suffix T, and then the radius was Ri and R naught, or little I, or capital O, little o, and then surrounding this was a layer of insulation. K suffix I was the thermal conductivity of this layer, and the radius of the insulation ring was R suffix capital I at the outermost. There was hot fluid flowing through the hollow pipe. So T infinity I and HI, T infinity out, H naught. This is ambient conditions. And the whole idea, so this is a ring of insulation material. The whole idea is to reduce the rate of heat loss, okay, by using insulation. And we did an energy balance, a surface energy balance, and we said that the rate of heat transfer across these different layers is the same from surface energy balance, and there is no energy generation whatsoever in any of these rings, and so I can draw a thermal resistance network. Okay? So this was the network. The outermost temperature was T infinity naught. This was inner temperature, which is the temperature of the hot liquid that is flowing through at a very fast rate, so that the heat transfer coefficient is very high too. Then temperature of this ring here, Ti, Po, T little I, Po, T capital I. The variable, the flow variable is the heat transfer rate, Q. And then the various resistances, where the convective resistances at either ends. So this is 1 by Hi, Ai. Then we also derived an expression for the thermal resistance to conduction for a radial cylindrical body, which was logarithm R naught by R little I, 2 pi L K suffix T, the thermal conductivity of the pipe material. Then I have the insulation ring, which is logarithm of R capital I, R naught, 2 pi L K I. That was the thermal resistance to conduction. And then the last one is thermal resistance to convection across the layer of insulation on the ambient, which is 1 by H naught, A naught. Keep in mind these areas are functions of the radius, unlike the plane wall problems. So Ai was 2 pi Ri times L, A naught was 2 pi R capital I times L. Okay? And then we wrote the expression for the heat transfer rate or the heat loss rate through the pipe. Which is Q T infinity I, T infinity naught. These are temperatures that we don't have a control over, they are the operating variables. And then the big thing there, 1 by 2 pi Ri Lhi, R naught by R little I, Kt, Ri, R naught, 2 pi L Ki, and the last one, 1 by 2 pi Ri L times H naught. Okay, so this was the expression that we obtained for the heat loss rate. This is all old news. We looked at this last time on Friday. Okay. And then we said, okay, we were given a range of the insulation material radius or insulation thickness. What's the thickness of the insulation layer here? Ri minus R naught. So thickness of insulation is Ri minus R naught. Of course, if I had a lot of money, I could have a very, very thick layer of insulation. If I had a lot of space available, I could have a thick layer of insulation. But most times, we operate under a tight budget. We have design considerations, space considerations. So one cannot just willy-nilly slap on insulation and have fun. Okay? So we need to design and see if insulation is a good idea in the first place. And which is what we did by plugging in the values for each of these parameters. We plotted the heat loss rate as a function of R suffix I. This is in watts. This is in centimeters or something. And then we get the following plot, a rough sketch. Which immediately rang some alarm bells, because what we are seeing is adding insulation initially is actually going to increase my heat loss rate, which goes against the purpose of using an insulation, right? And this value of the radius of insulation where the heat loss rate is a maximum is the critical radius of insulation, Ri suffix C. Ri suffix C, critical of of insulation. Keep in mind, when people say critical radius, it does not mean that it's a minimum. In this case, it's a maximum. So only if the radius of your insulation ring is larger than the critical radius will you start seeing some benefits from the insulation. Okay, that's something I want to point out. And it's quite evident from the plot. And what I want to do very quickly is obtain the expression for I suffix c, and then have a couple more plots, look at the basic idea of what's going on, and then move on. Okay? Calculus, basic calculus problem, I have a maxima or a minima, so I set my first derivative to 0. And to check if this is indeed a maxima or a minima, I can do the second derivative test. Unless you have all the time in the world, I don't want to do that. So, but first of all, to obtain our I suffix c, notice that the heat transfer rate is a function of these temperatures which are fixed, cannot do anything about them. These quantities here which are also fixed because of the convective heat transfer coefficient and the radius of the pipe, you're not going to mess around with the radius of the pipe. You're not going to mess around with any of the pipe details. So the only terms containing the radius of insulation is the term here, and believe it or not, right here. So which means if I write my Q as a function of the radius of insulation, then Q is some constant on the top, which is T infinity I minus T infinity naught, and in the denominator is what I have as the function Fri, which is all of this guy. So this bracket term is that guy. Which means if I'm doing the differentiation, I'm going to mess around only with the terms in the denominator. So to find critical radius, set dq dri is equal to 0. So that's d by dri of all of these terms. Once again, I'll leave the details to you, but here is what you'll end up getting if you perform the differentiations and so on. So this is C times df by dri by f squared. This is using the product rule or the division rule in differentiation. This is what you end up getting. The C cannot be 0, the denominator obviously cannot be 0, so the only thing that can be 0 is the differentiation of this particular term with respect to the radius Ri. And if I do that quickly, so this is d by dri of the denominator 1 by hi 2 pi ril or little I kt. Those terms do not undergo any differentiation because they are not functions of the critical radius. Then the culprits, and the last one. This is all set to 0. This term is unaffected. This is also unaffected. The terms that affect my game is this particular term here and the next one there. If I do the differentiation quickly, I end up getting logarithm. Differentiation of a logarithmic term is 1 by that particular term. So 1 by Ri by R naught. Then differentiation of Ri by R naught, which is just going to be 1 by R naught. And then 2 pi L Ki, that's the differentiation of the first term there. Then the differentiation of the second term, minus 1 by 2 pi L H naught R square is equal to 0. That is the differentiation of this term here. And this term here. Is that. And so, one can solve for Ri. Okay? In the exam, if I'm asking you to calculate the critical radius of insulation, you don't need to show me all these steps. You need to take the final results that we have from here and then check the numerical values, unless I ask you to do the derivation, which I'm not going to because I'll be having my notes posted on lecture card. Okay, so there's no point. So if I do the cancellations here, this is gone, 2 pi L, 2 pi L, Ri is a common factor. That's gone, and so solve. Ri, which is now going to be called as the critical radius of insulation, is quite simply the ratio Ki by H naught. Very elegant. Just two things. But don't let you fool that. Don't be fooled by this expression, because H naught is a function of a million things. Okay? And since it's a function of a million things, you cannot control this guy. So the only thing you can probably control is the thermal conductivity of the insulator material. So this is where your choice of the insulation material comes into play. So that's the design criterion. The function of the amount of cash that you have for the particular design product. People in the back, do you have a question? Question?
More practical, would H not also be a function of the radius itself?
It is certainly a function of that too. There is an inverse relationship functionality there, because it's a function of how large the surface is, which will account for the effect of the roughness of the surface interacting with the fluid interacting outside. Right. H naught is a function of T infinity naught. It's a function of the temperature of the insulation as well, the outermost insulation ring. So it's a function of several things. Okay, so in reality, if you unpack it, H naught is a function of T naught, Ti, the area that is available, right? Surface roughness, then viscosity, density, so many other things. And since it's mostly a challenge to find these things, what people do is they perform experiments and then we resort to using the empirical expressions to calculate the convective coefficient. Alright, so this is the critical radius of insulation. What is the guarantee that this is indeed the value at which the heat loss rate is a maximum? Second derivative test, or you can do the following. Okay? I'm going to plot. I think I did this very briefly last time, but maybe not elaborated on it. So plot this is Ri. I'm going to look at two terms that make an appearance in the heat loss rate equation. This term here and the other term. Okay? What we can understand is that if the combined effect of these two terms is going to end up being a very small value, the heat loss rate is going to increase. Which also means that if the combined effect of these two terms is a large value, the heat loss rate will reduce. So the heat loss rate is a function of the behavior of these two terms, and I'm going to plot them here. So term 1 is logarithm of Ri by R naught divided by that, and term 2 is 1 by 2 pi Ri H naught L. As Ri increases, the logarithmic function is going to start increasing in a nonlinear manner, and this is how the increase is going to be. For Ri is equal to R naught, logarithm of 1 is 0. So I start at R naught value, which essentially means I have no insulation. Then I start slowly increasing this. This is just going to keep climbing. Of course, the rate of increase is going to be slightly more sluggish as I keep increasing Ri by a very large value. Okay, this is term 1. If I plot the second term, which is term 2, you see that the term Ri, the variable Ri, is in a denominator. So if I increase Ri, that term is going to start dropping in value. So that behavior is going to be at loggerheads with the behavior of the first term. So this is term 2. As I increase Ri, that term decreases. But what is interesting to observe is that the rate of decrease of this term is greater than the rate of increase of this term until I reach an intersection point. Okay, so until I reach this point here, if I add up the behavior, 1 plus 2 is, this is 1 plus 2. So you see that the net behavior combined together tells you that I have a minimum of these at the critical radius, which means that the maximum heat loss rate actually occurs at RIC. And any insulation radius greater than RIC is going to start giving me some reasonable results. Okay, so once again, there are two terms that are trying to beat each other here. One is the thermal resistance to convection, the other is the thermal resistance to conduction, to the insulation ring. Initially, the rate of decrease of the thermal resistance to convection is higher than the rate of increase of the thermal resistance to conduction, and as a result of that, the rate of heat loss increases. Until I reach a critical value, which is Ri, C, this situation will continue. I will reach a maximum at Ri, C, which you can do the second derivative test and check and see if it is less than 0. That's going to be a maximum for me. And after that, the rate of decrease of this is lower than the rate of increase of the conduction term, so the conduction term picks up, and essentially my behavior is going to be governed by the size of the ring of insulation. Any insulation that I add after RIC is beneficial. Okay? I want to very briefly write these results down. For R less than or equal to Ri, C, Q, which is the heat loss rate, increases with Ri, and this essentially is that R convection out is greater than R conduction through the insulation material, and then for Ri greater than Ri, C, the loss rate decreases with Ri, R conduction I much larger than convection to the ambient, which is where we want. Alright, so that's the end of the critical radius of insulation. Very practical problem, something that we encounter in many applications. Very useful to have knowledge of this. The problem can have many variations. Instead of having a hollow pipe, I can have a solid rod with heat generation. And I would like to minimize the rate of heat loss as the heat is generated through that, and I would have an insulation ring around it. Okay, I have a question, please.
Yeah, so just to clarify, that RIC equation is only for cylindrical, correct?
Yes, absolutely, yes, of course. This is for a cylindrical body. One can derive something similar for the spherical body, so long as one can write the thermal resistance to conduction for a spherical body,
Thank you.
which can be done the same way that we did for cylindrical systems. Good point. All right. Yes, this question. 2
So-
minutes. Okay, first time.
Back to that graph originally with the heat loss, but no, the one on the top right.
Oh, yes.
Wouldn't the heat loss even at that point still be more than if there was no insulation at all?
No, that's what we found out last time in class. If I used the values that I substituted, I believe Q without insulation was like 115 watts, and then Q with insulation, I think was like 131, 133, 116, and then 115 and 113. This is for maybe 2 centimeters, 3 centimeters, 3.5, 5 centimeters, 10 centimeter insulation. This was without insulation, 115. This is with insulation. If I start putting a 2 centimeter radius of insulation, I'm actually increasing the heat loss.
Yeah.
Right. So that is the thing. The important thing to check is, okay, what is the heat transfer rate or the heat loss rate without insulation? Then you start saying, okay, I'm going to slap on some insulation and then start calculating what is my heat loss rate with insulation. I have to reach a point where the heat loss rate with insulation is obviously going to be lesser than this guy. And that's going to be from where my selections will start. Okay?
So the RI critical isn't the point where it's under 115 watts, it's just the point where it starts decreasing.
Right, right. So this is probably somewhere here is when it starts decreasing. You have a question.
I figured.
Yes, yes.
Why is it there when it starts decreasing? Wouldn't it be when it starts to go back down? So wouldn't it be between like 133 and 116?
What is where?
For our critical, if you were to,
Oh, right, right. It must be somewhere from yeah, I might have this. So somewhere here, one of those ranges here. I don't recall the exact numerical values, but I think you might see from last Friday's notes. I remember the critical radius of insulation. We can, for our problem, if I recall, Ki by H naught, I think Ki was 0.15 watts per meter Kelvin, divided by H naught was 10, so this was around 15 centimeters. Okay, so 15 centimeters is Ri comma C was 15 centimeters or something of that sort. Maybe H naught was 20. I don't know. But check those numbers. So if you have the numbers, you can calculate these values. Okay, and I'll post my solutions with the numbers as well. I did not want to spend time doing those calculations again. All right. Any last questions on critical radius of insulation? Yes.
Is it possible that that critical radius is actually less than R naught?
Right, so your critical radius has to be at least as large as R naught to make any difference in the problem.
But if the
Then you don't need a critical radius.
Okay.
Yeah, absolutely. Then it means that you'll have to start tinkering with the geometry of the pipe. Maybe reduce the radius R naught and then start putting layers of insulation. Okay. So we were looking at preventing heat loss, right, in the critical radius of insulation. Now we go to the other side of the problem. How do I increase heat loss? Which is by making use of fins. That is, how do I increase the heat transfer rate between a surface and its surroundings? Okay, so this is called heat transfer. From extended surfaces or fins and to understand how this happens, okay, I'm going to consider a surface just as it is. So here is a surface. Some plane wall, and I'm going to say that the temperature of this wall is TW, isothermal surface. Let's say that the surface area available for heat transfer between the wall and the ambient, which is T infinity in H. So A is the surface area or the cross-sectional area that is available for heat transfer. If I write the heat transfer rate between the wall and the ambient, so Q, convection is the heat transfer rate, and let's assume that T wall is higher than T infinity. In most situations, I want to design something that cools the wall. I want to design something that enhances the rate of heat transfer from the wall to the ambient. Okay, so heat transfer rate from Vol to ambient, and so Q is H times A times TW minus T infinity. This is no surprise. This is Newton's law of cooling. If I want to increase Q convection, what can I do? Yes.
You increase the area or the convective constant.
Absolutely. So I could either increase the convective heat transfer coefficient, or I could increase the area, or I could reduce the temperature of the ambient surroundings, or I could increase the wall temperature. I cannot mess with the temperatures. For one, I cannot change the temperature surrounding me, but we are very successfully doing it with global warming. I also cannot change the temperature of the ball. Those are my operating parameters. So the things that I can tinker around with are this convective heat transfer coefficient and the area that is available for heat transfer. So increase H, increase A. Ways to increase H: I can make the speed of the air surrounding the surface to be very high. I take a blower and I start blowing air across the surface, which is once again impractical because I have to invest money in it and I may not have the space for it. There are other factors that affect the value of H, and so just increasing the speed of air is not going to do it for me. And so the easiest way, within space limitations of course, is to increase the surface area available for heat transfer. Okay, so this is the most practical. And something that is really startling and stark is that if you go back to nature in all her glory, you look at the design of the Stegosaurus. The things on its back are essentially acting as cooling fins. They are enhancing the rate of heat transfer from the Stegosaurus body onto the ambient so that the body temperature does not go beyond a certain core temperature. Okay? So that's one of the best designs that is there. And there is a paper that I'll post on your Carmen page. It's very simple to read, 3 pages. It talks about how this convective heat transfer is taking place between the scales of a Stegosaurus and the ambient. Okay? Pretty startling. Alright, so that's what we are going to do. So increase the area of heat transfer, available for heat transfer, by extending the surface area, within space limitations of course. So keep that in mind. There are some downsides. You may increase the weight of the body by doing so. So which makes the idea that if you are increasing the heat transfer rate, then you have to make sure that you are not increasing the weight by a very large manner, and so you use very, very, very thin extensions so that it does not change the weight by a whole lot. Okay, so increase area A by using fins. And I'm going to draw a figure that depicts the same wall. This is a fin. And now you see the total area that I have available for convective heat transfer is this area A, this piece here. Then I'm going to have all of the surface area on the top of the fin, all of the surface area that you see on the cross section of the fin, all of the surface area on the bottom of the fin, on the sides of the fin, and also this guy here, which is absolutely much greater than the surface area A of the original surface. Okay, so all of this is going to increase my heat transfer rate so that I have a cooling requirement to be satisfied, and these are called as cooling fins. And of course there is nothing wrong in saying that they are heating fins as well, because if the ambient temperature is greater than the surface temperature, the use of fins will increase the surface temperature. by transferring by changing the direction of heat transfer. Our specification is for cooling requirements. All right. And many applications. You have fins in motorcycle engines. So engines, then air conditioning units, heat exchangers, silicon chips, they also require fins. We very briefly saw this silicon chip design a couple of lectures back where I drew the fins, but then when I did the heat transfer analysis I did not include the effect. Now we are capable of doing that. Okay, after a couple of lectures here. Alright, so we're now going to derive the fin equation. Okay. And to do that, I'm going to set up a coordinate system. So this is my fin figure here. X-axis, Y, and Z-axis. So the fin is also a solid body. Here is my question to you. What's the difference between a fin and a plane wall? Here is a plane wall. That's a solid body. Here is a fin. That's a solid body. So am I just adding an extra plane wall and saying and calling it as a fin? Yes, sir?
No, because the heat transfer is going through the width of it.
Well, I could do the same thing. I could have an extra plane wall and the heat transfer, conduction heat transfer still would be through the width of it. Yes, yes, yes.
Well, mostly if you're doing like one-dimensional, but like with the fins, it's going to be like from top and bottom and from the edge. So.
Very nice, very nice. That is the answer I was looking for. Excellent. So, you look at the direction of convection heat transfer. If you're looking at a plane wall, the direction of convection heat transfer is parallel to the direction of conduction heat transfer if I assume a one-dimensional heat transfer. We're assuming one-dimensional heat transfer, right? So the direction of heat transfer is this way. Q conduction, Q convection. They are parallel to each other. But if I look at the fin, the direction of heat transfer through the wall is in the x direction. Then this heat travels into the body of the fin where the conduction is taking place along the length of the fin. Once again, I'm assuming one-dimensional heat transfer. But importantly, the direction of convection heat transfer is in the y direction and the z direction, which are orthogonal to the direction of conduction heat transfer. Okay, so for a fin, Q convection is along the y and the z and is perpendicular. That's my symbol for perpendicular. Perpendicular to Q conduction along the length of the fin. All right. So we want to derive the fin equation. I will do it in a nifty manner. And I want to draw the dimensions of the fin first. So the width of the fin is going to be capital W. Then the thickness of the fin is little t. Then I'm going to assume that the length of the fin is capital L. And you will ask me, hey, you are doing this for a fin whose area of cross section is a rectangle. What if it is not the case? You just have to change only a few variables, change the way the area is calculated. Okay, because I'm going to make a list of assumptions now which will enable us to transform our equations to any type of a fin. What you are seeing here is called as a straight fin. In many applications you can have what are called as spin fins. So you could have something like fin fins which are in the form of thin pins. where the area of cross section could be circular, or it could be a varying area of cross section as well. There is nothing sacred about having the area of cross section a constant. Okay? And now I'm going to shade a couple of things here. One thing I already shaded. This area that I'm shading is the cross-sectional area of the fin, A suffix C. AC. Okay, in our situation, this is just W times T. This is for the figure I drew there. Then I'm going to look at the perimeter of this fin. That's of this cross section. So this is the perimeter. Perimeter is going to be 2 times W. Essentially, I'm adding up all the dimensions along the length of the cross-sectional dimensions. So perimeter P is 2 times W plus T. Then the first shading that you see is called as the base of the fin. So this is the base. Okay? The base temperature of the fin will be the same as the temperature of the wall, so that acts as a boundary condition for me. If I know the temperature of the surface of the wall, that's the entry temperature of the fin. The base of the fin capital B. And here are our host of assumptions. These assumptions are limited to the fin, not to the wall. Things can happen in the wall, we don't really care. We have the wherewithal to include all these effects. First thing, steady state. The E dot store is 0. No energy generated within the fan. That's another assumption. E dot G is 0. Okay? Then the third assumption is that the direction of heat transfer along the length of the fin is in the x direction. Is 1D along x, though in reality the direction of heat transfer can be along y and z as well. There is nothing that prevents it from happening. This is an assumption that we are making, and we will see that by making use of what we will come across as the lumped capacitance model, or the Biot number assumption, which you may have come across in system dynamics for transient conduction. We will make use of that assumption and then prove that that is indeed okay, that it's 1D. And I'm going to assume the cross-sectional area is a constant. And what I want to do is, I just want to draw the infinitesimal volume element taken from the fin, and then we will come back and complete this equation in the next class. 5 more minutes. So I'm going to consider a differential element of length dx. So that's a differential element of length dx. I'm going to take it out and draw it here. This is the x-axis. axis, and this is the z axis. So the dimensions of this piece here in a minute. Thickness t. Then the length along the x-axis is delta x. So this length here is delta x, and then the width is w. This is a differential element taken from within the fin. Okay. All right. There's going to be conduction coming in from the left side and then traveling along the length of the fin. So I'm going to have conductive heat transfer this way. So Q conduction at the face x, and then this is coming out as Q conduction along the face x plus dx, so right here. X plus delta x. That's conduction heat transfer across the fin. The area of heat transfer available is the cross-sectional area of the fin. And then all along the rest of it, because I'm assuming this is a cooling application, there is going to be convective heat transfer taking place. Okay, so there is going to be convection this way. So Q convection in the y. There is going to be Q convection in the y direction down as well. Then Q convection in the z. And likewise on this face. Q convection z. I'm going to write the energy equation, then we'll quit. E dot stored is 0, E dot in is 0, first law. E dot stored, E dot in, E dot out, E dot generated. So E dot in is equal to E dot out. This is essentially like a surface energy balance. This is within the fin. Okay. And if I look at the energy term that is coming in, the rate of energy coming in is Q conduction in the x direction. So Q conduction x is Q conduction x plus delta x. Watch this. Q convection in the y, Q convection in the y, both of them are going out. They are taking place along the same surface area. And so that's going to be 2 times Q convection in the y, plus 2 times. And by the same argument, 2 times Q convection in the z. On Wednesday, we'll come back at this particular point and we will continue after that. A quick question? Yes.
Wouldn't each of those have an area element too, depending on?
This is the rate of heat transfer,
Oh.
not the flux. Flux will have the double prime. So that's my next step. The area for Q convection Y is not the same as that for Q convection Z. Absolutely. Okay? This is the heat transfer rate, not the flux. Last question, yes.
So I'm a little confused on why convection isn't occurring on the x-axis at the end of the fin.
Oh, so I'm taking something from the interior of the fin, within the material of the fin.
I gotcha. I'm talking overall for the fin. You said convection in y and z.
Here there will be convection here as well. Absolutely. There will be convection at the tip. We'll see that if the fin is long enough, that's going to be kind of negligible in some sense.
Gotcha. Thank you.
But for this case, you're still not going to have convection there because I'm taking it from within the material. Thank you. Oh, from lecture 1 to today.